Yes. Yeah. As I mentioned, and Mr. Ajay also mentioned, the demand from a chemical engineer is increasing day by day. You are required to meet so much. You need to increase productivity, process efficiency if you are operating, if you are a plant engineer or plant manager. You need to increase the energy efficiency. There is a big effort in every industry to monitor and manage energy consumption because that is one of the most expensive inputs into the plant. Increase safety, whatever you do, you need to make sure that the inherent safety of the plant need to be increased, starting from the design stage, and whenever you make some retrofit or make changes, you need to make sure that the plant operates safely. And you also need to decrease the footprint. You need to make the size of the plant as small as possible through process intensifications. A lot of effort is being made on that line as well by chemical engineers. And, you need to remain carbon neutral. There is always people talk about how do you decarbonize your processes. Can we do it? The moment we use electricity, you find you already use some carbon in it, right? Every act of us, there is some carbon dioxide release. Is that right? So, but you can try to be carbon neutral. It is impossible. I wouldn't say impossible. It is possible to go as close as possible. So try to see what makes the plant or your process carbon neutral, and decrease effluents and meet environmental legislation. For example, the benzene levels in Euro 5 is less than about 10 ppm per day. Every time the new regulations comes, the refineries need to revise their plant operations so that they can meet. There are refineries which were closed because they were not able to meet this standards set by the countries or the European Union, etc. And also we need to look into sustainability through the circular economy. There's no more collect some resources, process it, sell it as a product, forget it. The product is used and thrown. Now we cannot do that. We need to get back the same product, used product, back into the process. We make things circular economy. And what helps in chemical engineers in meeting some of those demands? The one thing that helps us is the process or technical knowledge and your expertise, the domain expertise, without which nothing happens. You know everything except domain expertise, it's no use. Okay, you should be strong in your own domain, chemical engineering principles. Okay, understanding of the process behavior, the dynamics of the process. Whatever the process that you are operating, you should know how it dynamically behaves. Unless you know how it is going to behave, you cannot take any control action on it. Then accurate mathematical models to predict the behaviors or events. Okay, in controlling the plant, in olden days we have all been looking at an error that has already happened, then you take the corrective action. Now this time, with the introduction of all these DCS and automatic control systems, and with the introduction of predictive controllers, modern predictive controllers, you are actually predicting what would happen next 5 minutes, 10 minutes ahead of time, and you are taking a control action for that based on that output. Right? So you need mathematical models to predict the future and take the correction so that you stay on course. It's like driving a car on the road. You see there is a turn and you turn it. Okay? You are not hitting somewhere and then you turn. So that's feedback control. So this is predictive control. You predict and then take action. We normally try to use simple models to describe the reality, and those simple models could come from your first principles, the fundamental models, which is white box. You have understood whatever you have understood, applying the principles of conservation of mass, energy, momentum, and all your constitutive relationships. You build your model and you simulate right? That is, you know the reaction kinetics, everything is known. It's white box. There are certain mechanisms, reaction mechanisms, which are not understood, and that you try to take data, you run an experiment, you collect data, determine parameters like reaction rate constants, then it becomes semi-empirical, phenomenological models. You know the mechanism, but you do not know the rates, you get it from through experimental data. Then the last one is empirical models. Empirical models are like black box. We do not know what goes. We know what goes in and what comes out. We do not know what happens inside. Right? It's no mechanism. We do not know anything about the process, but we know there is an outcome. And data science relies on this, the black box approach. Takes all the data that's available and processes it. And these models, except the empirical models, are limited to the processes that are modeled. Suppose if I take the first principle model, I model the heat exchanger for a normal heat transfer, fluid flow and heat transfer, and there is a fouling that happens. If the fouling is not modeled, then you are not simulating the heat exchanger correctly. So I would call, if there is no description of the fouling rate inside the model, that is what I call an unmodeled process or mechanism. So these first principle and phenomenological models can only describe, simulate the behaviors you know you have modeled. And it is impossible to capture all the mechanisms, all the processes, sub-processes which take place in the first principle models. We always make assumptions. How does our model become simpler? Make assumptions. Make another assumption, reduce one more equation. Isn't it? The assumptions, actually you are neglecting some of the sub-processes. Alright? So therefore, the fundamental models are limited to those, under those assumptions. You always have to validate those models with keeping in mind what are the assumptions that under which the model is built. Okay. Next comes the digital revolution. It started around 1980 with the introduction of internet, and afterwards with the introduction of all your mobile devices, social networking, big data and computing clouds, and people generate more and more data on Earth today. It's based on a study in 2020. We are generating 1.7 megabyte of data every second. Okay, every movement of ours is captured. If you hold your handphone and you put it on a tracking mode or a GPS on, your movement every millisecond is captured. You are generating, you do not know. I cannot say that I have not been to KLE this particular day. Right? Everything is captured and the data is stored somewhere. You do not know. We do not know where it is, but it is there. Okay? Availability of inexpensive and powerful computing devices has helped us in developing the field of data science. And in parallel, I'm coming to process industries. In parallel with the developments of digital devices, the instrumentation sector and data acquisition sector also grew tremendously. The availability of inexpensive digital devices, modern sensors gave rise to the generation of massive digital data in industries. And for example, how we collect all those data is through SCADA in process industries, which was introduced in the mid-1970s. It's nothing but a control system architecture comprising of computers, network data communications, graphical user interfaces for high-level supervision of machines and processes. Let's see how it evolved over time. From 70s, it was like first gen monolithic, just one DCS. It just sits in your plant and operates. That's it. In the second generation, it became distributed. You have a big plant and you have distributed DCS, smaller DCS in different sections of the plant, operating independently. And in the third generation, they all got networked. That means one DCS to another DCS, there is a network. Now the DCSs in the fourth generation, they become web-based, which means that you can access this DCS from anywhere. Okay, if you are connected to a plant operating system now, you can always see what is the data, what are the production rate, what is the temperature in the reactor, anywhere. So it's a very clear indication that access to data anywhere, anytime, it's unlimited. And that's what makes us a possible candidate to use data science to make a small increment in your process efficiencies. Our ability to generate large data sets not only by the operating plants, we are also generating data through, one is continuous acquiring data from the operating plants, the rest is, high throughput experimentations. A lot of experiments in the research laboratories, high throughput, they generate a lot of data over time. Large lab scale observational studies, like the study that we did with Dr. Umesh and following, we conduct experiments for 10 days using a probe to study the falling of the crude oil, okay, at high temperatures. We collect data every second. So that way we produce a lot of data and massive simulations. Nowadays you have a lot of simulation software like ANSYS, Fluent, CFDs. You generate a lot of data. Every node in your object, in your pipeline, in your equipment, you have data, your temperature, pressure, flow, everything. It's even velocity in 3-dimensional. It's as a vector. You generate a lot of data. It's a decades of modeling, simulations, and experiments have resulted in a massive amount of data, and it's always expensive to gather large amounts of data from one source. Suppose if I want to develop or generate data consistently with the same accuracy, I need to do the experiments with that equipment all the time, collect the data. Is that possible? Collect large amounts of data from a single equipment consistently? It is not possible. But you have data related to that elsewhere. There are databases. People do experiments, publish, but they come from different sources. So they are not consistent data. They are not being collected with the same conditions. Okay? So that we started using the big data here, the data that comes from different sources. Okay? It's a variety of data. And if you look at this, one example is this, the chemical engineering, the Journal of Chemical Engineering and Data. It started in the year 1956, publishes only data. Data on thermophysical properties and equilibrium. Okay, you go into this, you'll always find it. And there's a lot of data available which you collect. Suppose if a VLE of benzene and toluene is of interest to you, you pick the data from there and you use it in your, as a database for your data science applications. And there are open source databases, and there are some commercial databases. The new trend is to seek information or knowledge from the data. That means we are actually trying to pick out the experience. We try to pick out the experience through the data. An option of making predictions from experience as an extra modeling toolkit. Other than understanding the process, writing down the equations, applying our fundamental principles of chemical engineering, you can also learn something more by analyzing the data. The data science is an area for chemical engineers to resort to learn insights into the processes, businesses, and even extract certain features or behaviors which are not evident, which are not explicitly seen. In daily day-to-day operations, you are collecting a lot of data, you never analyze, and you do not know certain thing is happening in the plant. But if you collect all the data, try to analyze, apply data analytics techniques, then you will see there are some new features that's actually happening. So it is, the data science is an intersection of statistics, data management, visualization, machine learning, and software engineering. So everything needs to be there. So it is not that you do every part of it. Your part of it will be mostly in the machine learning, where you will be able to input your domain expertise and improve the accuracy of that particular model. The rest is all carried out by other people. So we work in tandem with other engineers, other fields. So it's becoming increasingly important due to huge increases in the amount of data being collected, reductions in the cost of computer hardware, advances in data analytics, algorithms. There are new algorithms being generated, being developed by the researchers, and there are a lot of open source codes which are available for those algorithms, and increased availability of powerful software tools, free. So what is AI and ML? What is artificial intelligence and what is machine learning? We go a little deep into the data science. AI, artificial intelligence, is the ability of machines to perform. It's the machines to perform tasks that are generally linked to the behavior of some intelligent beings like us, humans. So can an AI operate a plant? Yes. It has all the intelligence that you have to operate a plant. And who provides those intelligence? It's you. Where that intelligence comes to you? Through your experience, years of experience. Okay? It is not just the data alone with which you can build an AI, and that needs a lot of your input into the AI. Okay? So machine learning models are basically statistical or mathematical models in nature that can learn from experience and discover patterns in data without the need for explicit rule-based programming. Like we don't need to write programming like I want to solve a dynamic first-order differential equation. I want to solve it using your Gaussian method. You need to write a program in C Fortran, right? This is rule-based. But here it is not rule-based. It's not explicit. Okay. In other words, machine learning is any method in which correlations within data sets are implicitly modeled. Okay? And machine learning is a subset of AI, artificial intelligence. Important subset. Starting with the data management, which is the foundation for data science. If you cannot manage your data, acquire data, store it, process it properly, sort it, then you can't build successful machine learning models over that. Tools and methods to organize, sort, and process large, complex, and static data sets. And it enables real-time processing of streams of data from sensors, instruments, and simulations. You can collect from multiple sources. There are platforms which are available to collect data from multiple sources and then stream process it. And my company is the one which gives a platform for such stream processing of continuous data. The way data are organized, stored, and processed significantly impacts the performance of analysis, ease of sharing, and visualization. There are many ways and many methods of doing this, and there is it's very difficult to say this particular platform provides the best solution. There is always plus and minus in each one of them. And to understand where we started with this databases, data management, we started with Lotus 1, 2, 3. I don't know if the people sitting behind, you have heard of Lotus 1, 2, 3. It's all forgotten now. It was operating under the disk operating system, DOS. But definitely you know MS Excel, Microsoft Excel. Are you? Have you seen what are the capabilities of Microsoft Excel? None of us are using or we even know the capabilities that is present in MS Excel. You can do anything.
Hardly use it.
You hardly use it. You can do anything. If you have the data, you put it in cells, you can do anything. Can you go back and see, open your MS and you look into the add-ons? There are so many add-ons which are available for you to explore the data. You can do modeling. You can do machine learning there itself. You can connect R or Python. Okay? You can do optimization. You can do co-fitting. Everything is available in Excel. Please, that is the easiest at no cost. It's available with your Windows system, right? It's at no cost. You try to Utilize that as much as possible. Then you go for some specific software for a particular operation. The only problem with the Excel, it's limited to two-dimensional data. If it becomes three, you can circumvent it. But if it becomes 4 and 5-dimensional, it becomes difficult to. You can still work with Excel, but you have a lot of skill to do that. But it's difficult to interpret and things like that. Okay. So it's difficult to extract such set of data for programming and programmatic access for external tools. Suppose I buy an external tool that supports some of my IoT applications, and I have the data in Excel. It's very difficult. I don't say it is impossible. You can do that, but it's quite difficult to extract a subset of data within the reasonable amount of time, because everything has to be done in the order of milliseconds or even nanoseconds. And then came relational database management systems, or DBMS. Its data is represented by two-dimensional tables linked with identifying descriptors, and you can access the data with SQL using SQL. And you can make complex queries involving relationship between the tables themselves and data within the tables. And there are a lot of open source RDBMs available in the web, in the internet. One is PostgreSQL and MySQL, and the other available tools are like Oracle Data Management Suite, SAP Data Management, IBM InfoSphere, Microsoft Master Data Services from Azure, SQL Power BI, Amazon Web Services, AWS. There's a lot. You just need to get accustomed to how they operate and start using it. How about the computing infrastructure? You have all this software. You need a device to do the computations, right? The data storage sophistication has steadily increased, and new challenges related to the analytics has arisen. What are they? They are like, if you are using a single desktop or a high-performance computer with tons of process cores, lack the power required to perform computations with large and complex data sets. You have millions and millions of data points, and you want to process using your desktops or a powerful server, high-performance computing devices. It becomes very difficult. So what is the solution for it? We have massive amount of data we want to process and get something. Okay? A cluster of computers with capabilities to frequently exchange large amounts of data. These are cluster of computers which are tightly integrated. They exchange information between each one of them. Okay? But they are very expensive. So what are the cheapest way? There are something like Apache Hadoop. It has a rich software ecosystem. It works on a collection of loosely coupled computers. Okay? It's inexpensive, like the ones which are provided by AWS and Azure platforms. Okay? Moving on to artificial intelligence. It's a rule-based, in 1980s, it's a rule-based expert systems. We used the term expert systems before. Now we don't call expert systems, we call artificial intelligence everything. Okay? It's the simplest form is the rule-based expert systems in 1980s, and the field of chemical engineering started to adapt after that the clustering algorithms, genetic algorithm, and especially the artificial neural networks. People talk about ANN, artificial neural networks. For every simple type of job also we are using artificial neural networks. Artificial neural networks try to mimic our brains. They contain input layers, output layers, and some hidden layers. They are actually trying to map the input and output. They are trying to map the input and output through a relationship, a non-linear relationship. Okay? And the parameters are mainly the weights attached to each neuron and the bias and the activation function that captures the non-linearity of the data. And if the artificial neural network is simple architecture, 1 or 2 hidden layers, we just call it ANN. Okay. If you have many layers, then we call them deep learning techniques. The many layers of artificial neural networks tries to capture all the features of the data and tries to select its own feature variables so that it can build an accurate mathematical model. Okay, just a schematic. Artificial intelligence is any technique that enables computers to mimic human intelligence in performing certain various tasks. Machine learning is a subset of AI. It includes all techniques that enable computers to learn from experience. And deep learning is subset of machine learning that allows models to train itself. The models to train itself based on artificial neural networks. It can select its own input variables. Moving on to the process data analytics, its techniques and tools for making inferences and decisions about operations and supply chain based on data from process systems. It is, as we have seen, it is statistical mathematical models. Machine learning models are statistical and mathematical models, and the tools are built to predict as a prediction model, an accurate prediction model, to predict the output or the events, or to uncover the hidden structures. Okay, this is called a classification. This is called prediction. So the categories of ML models can be classified as by purpose. I'm doing it for classification purposes. I'm doing it for regression, trying to get a relationship between the input and output. And by learning methodology, it could be called as supervised, unsupervised, active, or transfer learning. Mostly used are the supervised and unsupervised in the ML area. Very important thing here is that when I'm talking about domain expertise, if you want to develop an application for your own plant, then you need to know what type of input, what are the inputs that will help to build the machine learning model better. Okay, so the selection of the variables or features as the model input can have a significant impact on the model performance itself. Low number of features, that's you have less number of input variables, helps in reducing the computational time, the training time as well as execution time, and also they can provide a more accurate models. Sometimes you may have 100 sets of 100 input variables, you want to build a mathematical model based on that, but the variable that you try to predict only depends on 10 of them. The other 90 are not useful. So trying to identify those impacting variables. You have to understand the cause and effect relationship. So is this variable will have an effect on this? Include. If this variable doesn't have an impact, remove it. In data science, once you put the data, all the data that are coming from different sensors like flow, temperature, pressure, everything together, they don't carry that information. They don't carry that information. This data is temperature, this data is flow, this data is pressure. It's all data. Okay? If you are working with your own data, you know this column represents temperature, TIC 201 in degree centigrade. Okay? The moment the data is transferred to a machine learning algorithm, it is 201, that's all. Degree centigrade is lost. The information that it is temperature is lost. And we normalize, scale it between 0 to 1. Everything becomes 0 to 1. Because we don't want temperatures in the order of 200, 300, mole fractions in the order of 0.1, 0.2. The values get, these small values, if you use them as such, the small values will become insignificant. So we want to give the same importance to all data, so we scale down. So that is the data that we actually use in data science. User understand that. We are not using the actual values, and we don't give any importance whether it is pressure or temperature or flow. So normally the input layer consists of basic process parameters like pressure, temperature, flow, residence time, etc. The feed characteristics distillation curves. In petroleum industries, you will see TBP through boiling point curves and compositions, etc. They are all represented by numbers. When you have data in numbers, it's okay. But what happens if you want to include certain information which is not represented in numbers? That becomes a challenge. Especially if you want to apply data science in the field of molecular science. How do you represent the molecule in your data science analysis? There are a lot of things that you need to do. It's more challenging, and I'm just restricting to the macro side of it. I'm not going to the micro side. Okay? There will be difficulties in representing your data related to things like catalysts, molecules themselves, and so on. Okay? We have seen the machine learning models can be trained in supervised and unsupervised approaches. Under the supervised learning approach, the task is to define a model, to develop a model, accurately predicts the response variables, which we call labels, from a set of input variables. The inputs are called predictor variables of features. The outputs are called response variables or labels. And under the supervised learning approach, you need a training data set, and that contains a labeled data. A labeled data means there is an output variable, the response variable. Alright? And with this, you have a loss function, something like some of the squares of the error between the predicted values and actual values. Actual values are those labeled values. Okay? And you try to retrain the model in order to reduce this error. That's what we call loss functions. And by which you develop a mathematical model. Given a set of predictive variables, it's able to predict the response. Right? I just want to give an example of supervised learning in chemical engineering. I want to estimate the boiling point of a certain molecule using quantitative structure activity relationship. One. The predictor here is the number of pairs of atomic bonds that do not share the same atom. Okay? The response variable is the boiling point. So you have a database and you train a mathematical model or the machine learning model. And sometimes, so that you have all this input. Here I am just using one input for various molecules, and you determine the boiling points. As one input, one output, one feature, one labeled variable. But most machine learning models can have multiple features, multiple inputs. Then you get a feature space, and a value of a point, a value of a sample can be seen represented by a particular point in this feature space. The feature space determines the value of that particular sample. And the feature spaces can be continuous and it can also be discontinuous as well. The response variables can be a quantity, it comes as a value, it's a prediction, or it can be discrete. It can be like on, off, yes, no, true, false, low, medium, high, and so on. Okay? So they are like classification. You try to classify them into different groups. This actually summarizes the most widely used algorithms for supervised learning. If it is classification, these are the techniques. If it is regression, these are the techniques. And here we have a binary and multi-class. That means binary is two classifications, yes and no, and multi-class like low, medium, high. And for regressions, these are the ones. And you will find here, I'm not going to look at each one of them. You will find that artificial neural networks is there in every case. So if you are good at artificial neural networks, you can always have an initial model. And if that model doesn't perform well, then you can try to see a suitable algorithm, a better algorithm to work on. In an unsupervised learning, the goal is to identify a hidden structure in a data based on some feature set. You only have a feature set, there are no labeled variables. You have all inputs, no outputs. So we put all the data together and try to sort it out, work, manipulate, and see whether they fall into different groups. So if we can actually find grouping on some sort of a criteria, a matrix, then you classify them. Try to say this is a group that belongs to low, this is a group that belongs to high. Try to give names to them. Okay? No labeled responses in the training set and no loss function. There is nothing to optimize, but there must be something, and that something is that you have a specialized matrix for each case, and this is generally called falls under the clustering algorithms. It's a data grouped by some measure of similarity and info some sort of label for each one of these groups. And the factors describing the clustering strategy could be nature of similarity, something like distance metric, distance between two samples. Okay? Euclidean distance, the Manhattan distance, Pearson correlation, Spearman correlation, etc. can be used to try to minimize. These are the ones. There is no sum of squares of errors, but there are some distances that you can try to minimize in grouping together. If they can be high density, that means all the data fall into a small narrow range. The distance between them is very small. The clustering, you can also, the other factor is clustering algorithm, methods like centroid methods, such as k-means, density-based methods, self-organizing, and hierarchical clustering. These are all the names or the words which are given to you, terminologies. Please go back and Google, take textbooks and read. Okay? It's not possible to touch each one of them in this short lecture. And these are the techniques under unsupervised learning. Although you wouldn't find ANN everywhere, but you still have artificial neural networks in the density-based algorithms. Alright? And there is also one thing that we need to understand is that you can always, there is an algorithm that is available for you to reduce the number of features. Suppose I have 30 or 40 features, I want to see what are the most important ones. That is where comes dimensionality reduction. So for example, PCA, principal component analysis. Hope you have heard of that. The principal component analysis, if you run your data through the PCA, it will be able to give you the latent variables which capture as a combination of all the variables that you are given into, suppose you have 10 input variables features, and probably you can capture everything into 2 latent variables. Okay, so the important variables can be selected through this, and you can also, the PCA also gives you, it enables you to find the outliers. Okay, if there is a data, you try to group all of them together, and there is one always standing out. That's an outlier. So you can remove the curating of your data. You can remove all the outliers, the mistakes, the errors, the measurements which are faulty. Okay, you can remove that. And how do I do all the processing? Do I have to write a code for each of these algorithms? No. In those days, when I want to simulate a system, just a first order differential equation, I have to write my own code to get an algorithm to solve it. But these days, for every algorithm that is developed, the people also write the code, and the code is available open source. The codes are available. You go to Python, say for example, it's a programming environment which is widely used by data science engineers, like Jupyter Notebook. It's available for every computing platform, whether it is Windows based or Linux based, right? You have Python for that, and it's available in a convenient website framework. You can just open like a browser. You can start working on it. Okay? So all these that helps you in doing things faster is made available to you, and mostly free of cost as well. And another language that is being used for statistical modeling is R. It's a language and programming environment for statistical computing and graphics, and it provides algorithms for linear, nonlinear modeling, classical statistical tests, time series analysis, as well as classification and clustering. When it comes to applications in chemical engineering, as we said, data science for chemical engineers, let's try to understand where are all the ways that, what are all the ways that we can use data science in our day-to-day operations in a chemical industry. Start with prediction models for control applications. Model predictive controllers. In 1980s, the model predictive controllers came into existence, used all linear models, linear prediction models. And most of our processes, or almost all our processes, are non-linear in some way or other. Some are mildly non-linear, some are strongly non-linear. Right? A strongly non-linear process cannot be controlled by linear prediction models. Okay? And developing a non-linear model for such a process is a tedious job. And if you have the input and output data and run through your data science, you develop a regression model that matches the input and output, and that can be used. Those can be executed in milliseconds or microseconds. It's very fast. You can have accurate predictions as long as you do not cross the range over which your data was used. Okay. Process monitoring and statistical process control. You can always have this, enable this as a statistical process control. You can see the standard deviation of your variables, your temperatures, your compositions, which are more important than the compositions, continuously. Okay. And high frequency real-time optimization. People call real-time optimization is normally done in the hierarchy of computer control. We always call the real-time optimization very at the top, which we say is carried out once in a week, once in a month. Because these optimization problems uses mathematical models which requires a lot of computational effort. They require a lot of computational effort. Because the models are built with our knowledge, the first principle models, or the phenomenological models, which takes a long time for the solutions. But with the models, machine learning models built using data science approach, they can be executed very fast. That means instead of a week, I can do it every hour. Instead of an hour, I can do it every minute. So high frequency real-time optimization is possible with the machine learning models that you develop through the data science approach. Fault detection and diagnosis. This is a very, very important area in chemical engineering where the machine learning or data science is playing an important role. Okay? Even now, where industries have not adopted the data science, the faults are seen only after the pump stops, the heater fails, okay, there's no product, there is a leak, only then people start to react. And industries have started working on this data, their streaming of data. They try to follow the pattern. They try to develop mathematical models. They follow the patterns and identify the moment the process started to drift from normal operation. You identify even 1 week before something is going to happen. Next day you see it's a little more prominent. Then you know, with your experience, you know this is something is happening with the pump blades or coil or something. You try to find out and figure out so that you can always save your plant from unnecessary unplanned shutdowns. And you can always initiate some predictive maintenance into this. The classification algorithm provides a lot of input for this fault detection and diagnosis. And you can also build these models as digital twins. Digital twins are also mathematical models which runs in parallel, in real time with the plant. The same input is given to the digital twin as the input in the plant. And this model predicts, and you always try to compare between these two. And this model can also be used as a prediction model. That means you know ahead of time what the plant will behave like next day or an hour later and so on. Supply chain management is a big task in industries to managing the supply chain. Suppose you take a refinery, if say for example your crude is slated to come only today and you have been operating with the plant for a particular plant load, and if the next shipment doesn't come by tomorrow 6 a.m., you'll have to shut down the plant. And shutting down and restarting a plant of that size is a huge effort, and that requires millions and a lot of man hours. Okay, operating a plant is nothing compared to starting up a plant and shutting down a plant. Okay, there is no one way to start up a plant, but that could be a best way, and that is why your domain expertise comes in, tells you operate this plant, start up this plant this way. Even the plant needs to be designed properly. When you design an equipment, when you design a heater, you need to make sure that I can use this heater to start up in the shortest possible time. Okay, you do metal balance, energy balance, and take that as the basis. You design your plant where only I have a 10 kilowatt heater, and using 10 kilowatt heater will take 10 days for you to raise your temperature to the operating condition. Do you want that? I want to start up in 10 minutes or 1 hour or 2 hours. So 10 kilowatt is not enough. You need to keep in mind that 10 kilowatt is required only for normal run after it reaches its operating conditions. How do you reach there? So the plant has to be designed to reach for the startup phase as well. Okay, that's a very, very difficult phase in the plant operation, and the prediction models helps you a lot in determining what is the best way to start up. All your prediction models and digital twins will help you in deciding that. Supply chain management, as I said, and also business intelligence. Not only get technical insights into the plant, but with this data, you'll also get business intelligence. And we use this a lot for energy management. We look at how the energy is being used. What is the energy efficiency now? Where the energy is leaking. You can always find if there is energy somewhere leaking, you can actually get somebody to fix that problem. Alright? Our experience is that we have worked on building energy management systems for different petrochemical plants. In one particular plant, an ammonia plant, when we built the energy management system, energy monitoring system, the steam efficiency was only less than 60% in the plant. Till then, the plant management didn't know that they are losing so much of steam. And the moment our software went online, they saw everywhere the steam consumption, the steam efficiency utilization is less than 60%. Then they started to see where the steam is being lost. And the next turnaround, they removed all the steam traps, replaced, serviced, the efficiency went to 90+%. That means saving millions and millions of dollars. Okay? So analyzing the data helps in determining those process efficiencies. Just to give you an application where in process control, the machine learning models could be useful, start with inferential control, and this is a simple block diagram for an inferential control, and this is the inferential estimator is where the machine learning models would sit, and it takes the inputs, current inputs, and the measured secondary variables. An inferential control is used where a particular output variable cannot be measured online and is not available for you to take the feedback control all the time. Maybe it's like a composition where you take a sample and send it to the laboratory, analyze through your GC and come back. It takes 15-20 minutes before the results come in. But the process doesn't wait for 20 minutes. You need to take correction. How do you take? Can I take all the other measurements? Instead of the composition, can I take temperature, flow, pressure, all these, whatever there is available around, you build a model that predict this. That predict the composition.
Secondary measurement.
This secondary measurements. It's all secondary measurements. We call all the other measurements available as secondary and build a model based on that and use that for immediate prediction of those variables. Okay? So your machine learning models could sit as inferential sensors in the inferential control. The next one is predictive control, process control. The predictive control, especially nonlinear model predictive control. Nonlinear model predictive control, the nonlinear models are very difficult to build. Capturing those types of nonlinearities, understanding them is very, very difficult. Even if you can build nonlinear artificial neural networks, but training them, selecting the number of neurons, selecting the right type of activation functions is a tedious task. And with machine learning models, it becomes much more easier and it also becomes more accurate. Yes, please.
There we can use the PCA so that we can reduce diagnosability and then model for not linear. Whatever the data you generate,
Yeah.
PCA, apply PCA,
Yeah.
reduce diagnosability.
Reducing dimensionality does not reduce the nonlinearity. It's still there. There are two different aspects. Dimensionality, so you have 10 different dimensions, 10 different variables, but the process, the relationship between the input and output is nonlinear. Yeah. Okay. So here, the prediction models could sit here and here to help you. They give the fast executing, more accurate mathematical models. So that helps you in having your model predictive controllers. Model predictive controllers implementation everywhere in industries, it has been very, very successful. They were able to improve the control system performance significantly. As I said, fault detection and diagnostics is a very important contribution to chemical engineering through data science. You are actually training the faults first. You try to find out the fault. You know in the past, your experience. You pick the data. During this time there was a fault. Pick the data and train your model. So that trained model captures your fault. And likewise, like cooler total failure, valve total failure, pump severe leakage, hydraulic simulator total failure. These are different types of faults that can happen, and you train them. You can even simulate those data. It's not necessary that your plant should have gone through those faults. You can actually simulate those data in a simulator, in a model, and then use that to train the machine learning model for classification algorithms. Okay? And then the actual healthy data that goes through the algorithm, it passes through if there is no fault. If there is a fault, it identifies, it's a classification algorithm, and identifies this fits into either this category, this category, this category, and immediately throws that there is a fault that's happening. Okay? So likewise, you can have fault detection for every component, every equipment in the industries, especially the rotating equipment, the pumps, compressors are prone for faults. Moving on, I just want to introduce one case study which we worked as a joint research with Hitachi R&D division in Japan. This is a work which we carried out from 2012 to 2020. It's about 8 years of study. I just want to introduce in one or two slides how it helped us. We use a technique called artificial adaptive resonance theory, ART, to deep learn the patterns, the relationships, the correlations between the data of all the data we pick, every equipment we pick, we collect all the data for a long period of time. We build a model, train the model, and that model is used. And that model, when put into operation, just like fault anomaly diagnosis, it triggers there is a faulty situation, an anomaly happening. Okay? We actually did this work on a distillation tower, the CDU, crude distillation unit, involving the pre-heat exchangers, the distillation itself, atmospheric distillation, and a few units afterwards, including the strippers. It actually helps, it helps to improve operational efficiency. we collect the sensor data from the plant information pipe and from the DCS system, and it goes to our anomaly diagnosis system specifically developed for refineries, and it gives the alerts on any anomaly situation, and it can also identify the root causes, what causes this anomaly to happen. We collect sensor data. We actually didn't bring the actual data here, just for, I'm not actually authorized to share this information. So I'm just using some unlabeled data here. Temperature 1, temperature 2 flow rate, normal behavior, and in our software it's categorized into certain numbers, each category. So this is a normal behavior, this is a normal behavior, and when a new category is produced, then we call there is an anomaly happening. Okay, whenever there is a deviation from the normal operation, the algorithm will generate a new category of operation. That new category will tell you, and you need to go back and check what actually causes this. And in addition to that, we also have developed a software for anomaly propagation analysis. Suppose if an anomaly happens in this particular area, in this particular equipment, then our APA algorithm will tell what are the other downstream equipment which will get affected by this. It can affect this, it can affect this, it can affect these. So we try to identify the propagation of that virus. Okay? If a particular error doesn't have any propagation, it is only confined to the particular equipment, then you can take corrective action as soon as possible. But then if it's going to affect other equipment downstream, then it needs your immediate attention. Okay? That gives the priority for you to act on. This is how we actually built. This is the crude distillation column C1101. We have models for the middle body of the section, middle section, column bottom, compounds, the product, the bottom area, and also for the diesel side stripper. So we have developed many models. So hundreds of models we developed and put into operation in a plant. And this is actually being commercialized in Japan, and it's working very well in some of the petrochemical plants.
Are the models very specific, like because
Specific, they are very specific, particular to that equipment. If you do retrofitting of that equipment, you need to retrain the model.
will it suggest any action? What action to be taken, or any?
The prescriptive analytics comes with your AI. You need to build model for that as well. We have not, in this particular phase of research, we have not done the prescriptive analytics. It doesn't tell you what you should do, but it can identify the causes. I don't know if I have a slide. Yeah, I have a slide. So here, this is in the diesel stripper. We have a normal operation. We go away from normal at certain points, and we look at the data of all the sensors that is coming to this particular model. There are some ups and downs, but these ups and downs happen because of some disturbances or even by our control actions. So we don't call them as anomaly, we still accept that as normal operation. But when you see here there is something happening at the end of it, something went wrong and it already triggered an anomaly. The new category has been generated and it flashes out to the operator, there is a new category of operation, this is abnormal, please look into that. And it actually gives you the category pattern analysis as well. It tells you at this point for this particular category what variable is actually going out of range. There are two sensors which are actually giving more than their normal data. So once you know which sensor is actually showing you that abnormality, then you can try to figure out what exactly is happening. If they hit temperature going up or going down, you know what. At least it gives you a hint. This is where it's happening. Okay. So some points to ponder. I'm going towards the closure of this talk. some points to ponder. Well-trained machine learning models can make accurate predictions in a fraction of a second. It's very good for us, but bear in mind there could be failures. The inability to extrapolate is a major weakness of machine learning models. For that matter, any empirical models. Suppose I have an operation in a plant which runs from 60% plant load to 90% plant load. This is the data that I have already taken. I have trained my ML, right? This gives predictions only when you operate between 60 or 90% of the plant load. Suppose you go below 60%, or you go more than 90% or 100%. That means there is no data, there is no knowledge within the system or experience within that machine learning model that can predict in those ranges. So be careful. The ranges over which these models are limited to the ranges over which you train the model. Okay? If you find that my plant will here on operate at 95%, you retrain your models. Don't use the old models. Retrain the models. There are some techniques. I said supervised learning and unsupervised learning and supervised learning. There are some techniques whereby you can slightly extend the applicability of these models by what is known as active learning. That gives us, provides some new data. It adds on to the experience within the system, within the algorithm, and it can extend your operating range a little bit, not much. Okay? So being a black box approach, as I said earlier, the selection of model hyperparameters is very tedious. You need to have a lot of understanding of the process so that you can choose. Even for trial and error method, you need to know where to start. You need to know where to start. And that start would come with your experience. Okay? And extracting physically meaningful explanation for certain behaviors is infeasible. You try to extract some meaningful information. That means we want to interpret. Interpretation can be done with fundamental models very, very well. But with black box approach, making interpretations is very, very difficult. Okay? You want to get some insight, and you want to connect that insight with some mechanisms, mass transfer mechanism, reaction mechanism. It's not possible. That's why I said the data point is just a data point. It doesn't carry any other information about the data. Doesn't carry it is a temperature, it's a flow. It's in what units even. It's a data, and it is all brought between 0 to 1. Right? So be careful that you will not be able to give any meaningful interpretations. Okay? As a concluding remark, with data science and engineering, we are moving towards autonomous control. We were manual controlling the plants manually, and we moved automatic controllers. All the plants in today is, if you take large plants, they're all automatically controlled. They have all DCS. They have advanced process controls implemented in almost all plants. But during the pandemic, we have seen the engineers were not allowed to go into the plant, but the refineries have to run. And the refineries have to run at a lower capacity. There is no, because people are not moving, no consumption of fuels, so the demand is less. So when the demand is less, you can't run the plant refinery at the same load, produce, where do you store? There is a problem of inventory. So people started reducing. Okay, the turn downs are actually difficult phases of operating a plant. If it is 80%, 90% operations, very good. But if you ask your plant to run at 40%, 50%, it's very difficult. How do you control your pump? In 40 to 50%, there are certain sections that are no flows. It's very difficult. And it was operated remotely. Every engineer sat in their house, connected to the pipe, the DCS from home. That's why I said the data is available anywhere, at any time, unlimited data. Right? People were able to sit from home, see all the data that's currently happening in the plant, communicate with the one or two operators in the plant. remote operation. Okay, so it was made possible because of the pandemic. We could test our communication systems. We could test our internet facilities. It's all web-based now. Okay, if there is no web-based, I have no way to open the DCS in my computer, in my laptop. Okay, iPad is enough. The notebook is enough. You don't need a computer. And you can employ artificial intelligence for decision making. Now, if you can make your artificial intelligence more and more powerful, infuse your experience into those artificial intelligence applications, okay, which can circumvent any type of situation. It can think as if you are thinking. It has every knowledge built into that. Okay. Use of more and more edge and cloud devices like IIoT applications. You can always connect equipments, network equipments by way of information. You can optimize a distillation unit looking at a cracker unit. Or you can optimize a cracker based on the current feed to the distillation column. Okay. The one issue with all this remote working web-based applications is the cyber security. It's a great concern that plant operators are worried about all the time. What happens if someone hacks? You don't need to hack the entire system. You just need to have one communication protocol. It's good enough, by which you can close or open one control valve. It's good enough to destroy your plant. Okay? So there is always a potential threat of opening up with all this. People are working on highly secure networks, web or cloud-based applications to safeguard the process plants. Okay. I said I'm not above you all in this particular field. We have worked on certain data for the last 10-15 years, but we never termed its data science. We have built neural network models. We never called it machine learning model. These terminologies came of late. Okay, and a lot of changes, developments in technologies in terms of your algorithms, programming, how you use it in your computers and so on, happened in the last 5 to 10 years. Okay, so these are my references I relied upon for most of my talk. And do the right thing, even when no one is watching you, and that is called the integrity. Okay, we want engineers with professionalism, ethics, integrity. Never lose that. You will never gain back. Okay. With this, thank you very much. My contact details are here. You can pick from here. You can always communicate with me. Okay. I'm a guy. Always want to sit over there. I want to be one among you, not one out of you. Okay. Always feel secure among the people and comfortable. Thank you so much, and thanks to KLE Institute for inviting me here, and special thanks to Professor Umesh. I can call him Umesh with no doctor from liberty. Thank you so much, and have a good day, and a fruitful day. Please go and listen to all the talks, all those presentations carefully, learn something, carry something back.
Thank you, sir, for the informative session and raising this event. It's time for the presentations. I request all the participants and dignitaries to gather in the department. I request all the volunteers to lead the way. Thank you, Anil.
हाँ जाना चाहिए Zero के कुछ और otherwise you can go यार तो साथ में कितना just talk it for you guys
ನಾ 3:30 ಟಿಕೆಟ್ ಬುಕ್ ಮಾಡೋದು ಮಿಕ್ರೋ before 3:30 I need to inform.
okay
चलो
before 2 you can go next session अभिषेक कैसे सुना मेरे घर से अभिषेक को बुरा समझा